Welcome to our lesson on if-then statements, converses, and truth values. The most important thing is let's see if we're calibrated, which we are not. So we will do that very quickly. So in this video, I'm going to be going through some activities that we did in class about if-then statements. So I will write and we will look at my logic statements here. So let's start with an algebra one. If x squared equals 16, then x equals 4. Is this statement always true? It is actually not always true. It is false because x could equal negative 4. We would have another time that if x squared equals 16, not only could x be equal to 4, x could also be equal to negative 4. So in this case, this is my original if-then statement. My truth value is false. And here is a counterexample. A counterexample being something that proves that it isn't always true. If I rewrite my statement in if-then form, what happens then is I take this original conclusion and I make it my if. So if x equals 4, then I'm going to take my original hypothesis, my original if, and make it my then. Then x squared equals 16. And this is actually true because every time x equals 4, x squared is going to equal 16. So let's talk about our next one. If the degree measure of an angle is between 90 and 180 degrees, then the angle is obtuse. And this actually has a truth value of true, because every angle that has a measured degree between 90 and 180 is going to be a true statement. Now, let's write the converse. So I'm going to start with the word if. But what I'm going to do is I'm going to take my original conclusion, and put it as my hypothesis. If an angle is obtuse, then the measure of the angle is between 90 and 180. Then the measure of the angle is between 90 and 180 degrees. And that also is true. Since these statements are true both ways, both as the inverse and the converse, they make a good biconditional statement. And a biconditional statement also makes a good definition. So if I wanted a definition for an obtuse angle, this is a great definition. If an angle is obtuse, then the measure of the angle is between 90 and 180 degrees. So let's look at the next one. If two angles are supplementary, then they are a linear pair. So, two angles that are supplementary do add up to 180 degrees. And a linear pair does add up to 180 degrees. But does this mean this is always true? So can I think of an example where I have two angles that are supplementary and not a linear pair? So if I have a 40-degree angle over here and a 140-degree angle over here, they are supplementary. They add up to 180, but they do not make a linear pair. So since I have this as a counter example, this statement is false. So let's flip this around though and see what happens. If two angles, that's my symbol for angles, form a linear pair, then they are supplementary. And that is a true statement. Okay, that is a true statement. Whenever I have a linear pair, they are supplementary. Okay, because they're always going to form, their opposite sides are always going to make a straight line. Which brings me to my question, what would be a good definition of a linear pair? So let's talk about what a linear pair actually is. A linear pair, we know, a lot of you will say, well, it makes a straight line. Okay? And they're two angles. So basically, a linear pair are two angles that are adjacent, meaning they touch. They share a vertex, and their non-shared sides make a straight line. So let's talk about that. A linear pair are two angles. They're adjacent, so they share one side. And they share a vertex because they're adjacent. And their non-shared sides make a straight line. So this is one non-shared side. This is the other non-shared side. Now, because I just said that a good definition would could be written as a biconditional if I wrote, if two angles are a linear pair, then they are adjacent and share a vertex, and their non-shared sides is a straight line. So this is kind of an overview of what we mean by writing if-then statements. So we actually have conditional was the original if-then statement. Converse, as we've just been doing, we flip the conclusion to the hypothesis. Inverse and contrapositive, I've said, I'm not testing you on. It will be extra credit, so let me give you an example on how to do that. So I'm going to go back to, we talked in class about the original conditional statement. If it's going to rain, then I'm going to bring an umbrella. Okay? The converse of that was if I bring an umbrella, that's because it's going to rain. And this one isn't always true. If I say I always bring, if it's going to rain, I bring an umbrella, There might be times that I bring an umbrella and it's not going to rain. Like maybe it's really hot outside and I want some shade. The inverse is I take my original hypothesis and my original conclusion and I basically do the opposite of them. Which gets a little confusing because if my original statement was that I wasn't going to do something, then my inverse would be that I am going to do it. It's the opposite. But basically, if it's not going to rain, I am not going to bring my umbrella. And once again, that could be false. Because what if it's not going to rain, but it's going to snow? And I want my umbrella to keep the snow off of me. And then the contrapositive, if I'm not bringing my umbrella, then it is not going to rain. In this case, this statement would be true. Because if I'm not bringing my umbrella, then I know it's not going to rain. I also might not know that it's not going to snow or be hot or whatever the reasons I might bring my umbrella. But that should help you take you through what we did in class with if-then statements, with writing a converse, with establishing a truth value, with understanding that a biconditional makes good definitions, and with conditional, converse, inverse, and contrapositive.